Very well, now we start a new chapter. That is the discrete time Fourier transform. So the abbreviation is DTFT, the discrete time Fourier transform. And we are going to find the Fourier domain representation of discrete time signals. Do we know the Fourier domain representation of any other type of discrete time signals? The answer is yes. We know the Fourier series representation of discrete time signals. But those discrete time signals with Fourier series representations require some information. They need to be periodic. So for periodic signals, we have the discrete time Fourier series, and we know it. So it may be a good idea to try to extract the formula for the discrete time Fourier transform from the discrete time Fourier series. Suppose that we have a finite extant discrete time signal, something like this. Suppose this is 0, 1, 2, and this is minus 1, minus 2. Okay? It's just a discrete time signal with some arbitrary lengths, coefficients, and we need to find, so this is x of n that we're looking for on the axis of n. We need to find the formula for the discrete time Fourier transform of this signal. Now, the best way to explain this is to extend this signal like this. So this is our signal normally from 0, 1, 2, minus 1, minus 2. And let's assume that we are replicating it with a period of capital N. So at n we have the same 0 value. At n minus 1 we have this value, n minus 2 we have this, n plus 1 and n plus 2 we have these two values. And this periodic version, let's call it x tilde of n. It's just a periodically replicated version. It's not only two of these, of course. It is repeating itself to the right hand side and to the left hand side too, to both sides. This x tilde of n is a periodically extended version of x of n. Periodic version, and the period is equal to capital N, and we can write the formula for this periodic version x tilde of n in terms of its Fourier series coefficients, if we wish, like this. With a k running index of extent capital N, it can be 0 to n minus 1, 1 to n over 2 to plus n over 2, minus n over 2 to plus n over 2, whatever. So within this range, it is the Fourier series coefficients multiplied by the corresponding harmonic, like this. Okay, this was the formula that we already know. Now, by extending this formula, is it possible to obtain something related with the Fourier transform of the top shell, which is x of n, not x tilde of n? Now, from here, let's first write the formula for the Fourier series coefficient. That is 1 over capital N summation again in an extent of capital N x tilde of n e to the minus j k 2 pi over capital N n. Now the trick that we will use at this point for this formula is that within a range of capital N, within this summation range, x tilde of n is the same as x of n in the middle portion. So I will just write it like this: 1 over n, and from the same range, x of n, instead of x tilde of n, within that one period, it's the same as the original signal, x of n, e to the minus j k 2 pi over capital N, n. And at this point I will make a definition. This denominator, capital N here, if I multiply with AK, I will have n times AK. This is a new entity which is related with the Fourier series coefficient, is equal to summation. Now, do you agree with this formula? Instead of within the range of capital N, I am writing from minus infinity to infinity x of n e to the minus jk 2 pi over capital N n. If I write it like this, will it be the same formula? The answer is yes, because although the original summation was within from minus n over 2 to plus n over 2, since x of n is all zeros afterwards, I can easily write it from minus infinity to infinity, and it doesn't change anything because this x of n is valid only from minus n over 2 to n over 2 anyway, right? It's over there. So they correspond to the same formula. The top one, the second line and the last line, they correspond to the same formulas. And at this point, I will make another definition, and that definition is this 2 pi over capital N. I will have to replace this. In fact, it's not only 2 pi over capital N, but k times 2 pi over capital N. As n goes to infinity, now that's the trick, okay? In this second figure, this is periodic with capital N, but the original one is not periodic, it's standalone. Aren't they mathematically the same if I take the limit that the period goes to infinity? As n goes to, capital N goes to infinity, it means it is aperiodic, because the period will become infinity. Is that okay? That's what I'm trying to do. I'm trying to take this second portion to infinity to make it this thing, the periodic thing, exactly the same as the aperiodic one. That's how I do it. I'm stretching the period to infinity. So I will stretch this capital N to infinity. And as we do that, 2 pi over capital N will become arbitrarily small. As n goes to infinity, 2 pi over capital N will shrink down to 0. That will go to such a small entity that it's something like d omega. Okay, so 2 pi over capital N will go to an infinitely small entity, a discriminant. Okay, that is d omega. And as you see the summation that we have over here, by the way, okay, that's for with the introduction of k here, k times 2 pi over capital N, I can define infinitely many very small entities, and k varies from minus infinity to infinity, by the way. So as k varies from minus infinity to infinity, k times 2 pi over capital N will stay in a reasonable limit. So it's like infinity times 0 ambiguity. But this infinity times 0 ambiguity will go to the so-called frequency. Because originally it was like this, wasn't it? In our Fourier series representation, what is the frequency, the corresponding frequency of the harmonic? Do you remember that? 2 pi over capital N was the fundamental frequency, and which was omega 0. K times omega 0 was the frequency of the harmonic. In fact, we were drawing the impulses on those positions, on the frequency corresponding to k times omega 0. So what I'm saying is k times omega 0 is the frequency, omega. And the substitution, the replacement that I will do in this expression is that k times 2 pi over capital N, I'm going to replace it by omega, which is the frequency. So N times AK will be equal to the summation N from minus infinity to infinity x of N e to the minus j omega N, not k 2 pi over N times N. I'm going to write it like this. Well, this you can write it like this. Omega is equal to k times 2 pi over capital N at this frequency, if you wish. You can write it like this. And the whole expression will correspond to the Fourier transform, which will have a representation x of omega. It's not in terms of k anymore, any discrete terms of k, but it's in the continuum case x of omega, which is the Fourier transform of a discrete sequence x of n. And from here you may feel that I'm not giving any proofs or anything. I'm trying to emphasize where you can extract or reconstruct the Fourier transform expression. We can feel that the Fourier transform, and I'm writing it as x of omega for the time being, is equal to summation n from minus infinity to infinity x of n e to the minus j omega n. You can say it like this. And if you check back your previous notes, you will see that this is not the first time that you see this formula. Previously, we were using this to find the frequency response of a discrete time system. Do you remember this formula that we used already? H of omega is equal to summation n from minus infinity to infinity h n e to the minus j omega n. This was a formula that I gave you already while we were covering the Fourier series representation. And you had to use it in order to find what is the output of the system. If the input is this discrete time periodic signal, what are the Fourier coefficients of the output? Do you remember how to do it? It was like this. And if you don't remember it, just please check back your notes and you will see this formula. In fact, in order to remind you better now, I was telling you like this. It's not h of omega, but for some reason, it's in this form. It's in this e to the j omega form. H of e to the j omega is equal to the same summation. But e to the j omega inside the argument, h of e to the j omega means nothing. It's the same as saying h of omega. It's a function of omega. But the representation is like this. It's like it's like questioning why were we telling in the continuous time Fourier transform, what was the notation of continuous time Fourier transform of x of t? What did we say? We said capital X of j omega. Why the hell are we saying j omega over there? Okay, it's just a notation. It's a function of frequency. Because of that, why the hell? Now this time we have even more. It's not j omega, but it's e to the j omega. H of e to the j omega, or x of e to the j omega. So the relation is, for convenience, this. Capital X of e to the j omega. This is the discrete time Fourier transform pair. And the discrete time Fourier transform formula is this. Okay, the top box that we have. But of course, there is a slight reason, again, that we already know. And I hope that you will remember. This e to the j omega has a meaning because the discrete time Fourier transform, or this filter h of e to the j omega, was repeating itself in 2 pi periods. Do you remember that? The frequency response of a discrete time system was 2 pi periodic. So if you have a low pass filter, some shape, some rectangular shape around 0, then it must repeat itself at 2 pi. and then at 4 pi. Do you remember that? We were discussing these things previously. So since it is 2 pi periodic, perhaps this x of e to the j omega expression, this e to the j omega expression is giving us an idea about that. Because the Fourier transform in discrete time is in terms of not j omega, but it's in terms of e to the j omega, which makes it automatically 2 pi periodic. E to the j omega is 2 pi periodic. And again, just like we did in discrete time Fourier series, you must always remember that if I ask you to find the discrete time Fourier transform. What is the discrete time Fourier transform of this x of n? I give you an x of n, and I ask you the Fourier transform. And you find something, some solutions, a formula in terms of frequency, in terms of omega, and say, sir, this is the discrete time Fourier transform. So the first thing that you have to verify to yourselves is that thing that you find 2 pi periodic? If it's not, then it's the wrong answer. Okay? Don't bother giving it to me. You did it wrong. It must always be 2 pi periodic. Let me make a quick jump to the inverse transform formula. The inverse transform formula will be a little bit more complicated to derive because the summations will turn into an integral, and the 2 pi over n expression will be like the omega of the integration, which is quite complicated. But the inverse Fourier transform formula is what you need without knowing the way to extract it. If you're curious about that, it's in the book, by the way. So we can always discuss that with the curious students. But for us, for the time being, what we need is this formula. This is an integral to find the inverse discrete time Fourier transform, or the discrete time inverse Fourier transform. This 2 pi underneath this integral expression means that the integration limits is with the length of extent of 2 pi. It may be from minus pi to pi. It may be from 0 to 2 pi. It may be from pi to 3 pi. So the duration of the integral is 2 pi. Okay, that's what it means. And clearly, capital X of e to the j omega inside the integral corresponds to the discrete time Fourier transform of x of n. So the whole formula is the inversion. Let me write again the Fourier transform formula underneath. And then put these two things in a box. The top one is the inverse discrete time Fourier transform. The bottom one is the discrete time Fourier transform. And just like in the case of continuous time Fourier transform or Fourier series counterparts, this e to the j omega t or e to the j omega n things here and here, they are just conjugates of each other. In the Fourier transform, the complex exponential is with the negative exponent, e to minus j omega n. In the inversion, it's positive, e to the j omega n, e to the plus j omega n. They are just conjugates of each other. They are always like that. If you check back the previous formulas for Fourier transform and inverse, this is what you will see. So let's put an exclamation here. This discrete time Fourier transform is always 2 pi periodic. Okay, this is something that you must be careful about. From this formula, it happens to be like this. Now, it's not very difficult to see it. Why is it always 2 pi periodic? As you see, e to the j omega is a combination of e to the j omega n's. Do you see that? For n is equal to 1, for example, this will be e to the minus j omega when n is equal to 1. This here. When n is equal to, in this summation, running summation, when n is equal to 1, this will be e to the minus j omega. When n is equal to 2, it will be e to the minus j2 omega. When n is equal to 3, it will be e to the minus j3 omega. Now, e to the minus j omega, e to the minus j2 omega, e to the minus j3 omega, e to the minus jk times omega in general. They are always 2 pi periodic. And all these expressions are multiplied by some scalars. They may be real or complex scalars, and then you are combining. So what are you combining? You are combining lots of 2 pi periodic signals. Therefore, their combination is of course also 2 pi periodic. That's always in the form of summation of complex exponentials that are all 2 pi periodic on the omega axis. Now let's see one trivial example, the first discrete time Fourier transform example, and see whether that is the situation or not. Will this formula give us what we expect? X of n is equal to a to the n u of n, where a in magnitude is less than 1. Why do I restrict this thing to be less than 1? Because I want it to be a convergence sequence. But if a is greater than 1, then a to the n will diverge, it will below 1. So we don't want that. So a is less than 1, and this is our discrete time signal. It's clearly non-periodic. Therefore, we don't have a Fourier series. We are looking for the discrete time Fourier transform. What is the discrete time Fourier transform? It's from the formula. Capital X of e to the j omega is equal to summation n from minus infinity to infinity. Inside it, I write x of n, which is a to the n u of n. And then I put e to the minus j omega n. That was the formula for the Fourier transform. And this u of n forces my summation to start from 0 and go up to infinity. Because n is less than 0 will make u of n to be 0. So we can write it like this. N is not from minus infinity, but it's from 0 to infinity. Then a to the n times 1 is a to the n, e to the minus j omega n. Now we can make some combinations of this summation, put into some parentheses, n from 0 to infinity, a times e to the minus j omega, I will say, to the power n. Do you agree? A to the n, e to the minus j omega. That is a times e to the minus j omega in parentheses to the power n. Now what is this summation? It's an infinite series summation. Think of it like this. Inside this parentheses, let's give it a name. Let's call it C. Okay. What is n from 0 to infinity, c to the n? This infinite series sum formula, power series, always. What is this summation? You still 1 over 1 minus c. Yes, 1 over 1 minus c. 1 over 1 minus a times e to the minus j omega. It's 1 over 1 minus c. But of course this summation converges to 1 over 1 minus c as long as the magnitude of c is less than 1. If it converges to this. If it doesn't converge, well, we have nothing. We don't have a Fourier transform then. It violates the famous Dirichlet conditions. So 1 over 1 minus c is valid if the magnitude of c is less than 1. Is the magnitude of c, this top thing, is the magnitude of this less than 1? A times e to the minus j omega. What is the magnitude of it? It's a complex number. What's the magnitude of it? the magnitude of it is the magnitude of A, because the magnitude of e to the minus j omega, or e to the j something, is always 1. It has one magnitude. It is just a rotating magnitude 1 complex number. Its magnitude is always 1. So the magnitude of C is the magnitude of A. It doesn't depend on omega. And in the beginning of the question, we said that the magnitude of A is less than 1. Therefore, the magnitude of C is automatically also less than 1. That's why the whole summation converges. And the converging result is this. The question now is this thing 2 pi periodic? Well, of course it is. But how come? We would expect something in the form of e to the j omega combinations, but the e to the j omega or e to the minus j omega, whatever, is in the denominator. Does it affect the 2 pi periodicity? And the answer to that is no. If something in your denominator, 1 over or a over something, the denominator part is 2 pi periodic, and the numerator is constant, for example, 1 over 2 pi periodic signals are also 2 pi periodic. They change with respect to the period of the denominator. So what you will be looking for is the following. Look for e to the j omega or e to the minus j omega in your expression. Look for it. If you can find it in the denominator or the numerator, or if you find the combination of several such complex exponentials in the denominator and in the numerator, if everything is in this form of e to the j omegas, then you are safe. You can say that it is obviously 2 pi periodic. And this one is also 2 pi periodic. And if you want to draw, this is x of e to the j omega. If you want to draw, for example, the magnitude of it, what you will find or what you will discover is something like this. For a between 1 and 0, let's say, let's assume that a is positive, because when a is negative it will be a little bit different. If a is positive, then this shape will look like this. It will be at omega is equal to 0. Let's find what the value is. When omega is equal to 0, e to the minus j omega is e to the 0, which is 1. So we will have 1 over 1 minus a. 1 over 1 minus a. Let's assume that it's this value. What kind of a we can think of? Let's say a is between 0 and 1. Let's say it's 1/2, 1 over 2. What is 1 over 1 minus a half? 1 minus a half is a half. 1 over half is 2. So this value is 2. Let's assume 1 over 1 minus a. That's the value. Now let's come back to, or let's come to pi frequency. When omega is equal to pi, what is e to the minus j pi? It is minus 1. When it is minus 1, 1 over 1 minus a times minus 1 will come into the picture, which means 1 over 1 plus a. So what is 1 over 1 plus a half? It is 1 over 1.5, which is smaller than 1. This was originally 2, and now it is 2/3. 2 over 3 sort of thing. So it's a smaller value, something here. When it comes back to 2 pi, at 2 pi, e to the minus j omega will again be 1, just like 0. So it will come back to 1 over 1 minus a. By the way, this point that we're talking about is 1 over 1 plus a. And at minus pi, it will come back to here. At minus 2 pi, it will be again a large number. So the figure that we're looking for is probably looking like this. So that's an oscillation with a period of 2 pi clearly. Now, is this a low-pass signal or a high-pass signal? Which one would you prefer? Band-pass, low-pass, high-pass, or nothing? Depending on the value of A, it's a low-pass signal. It's a low-pass signal, especially if A is greater than 0, or positive A, like this. This one is a low-pass signal. Why? Because this position around 0 is the low frequency, and the response around those low frequencies is large. Whereas, where was the high frequency? Do you remember? The high frequencies are around pi and minus pi, and odd integers times pi, like 3 pi, 5 pi. So these are, this portion is the high frequency. Pi is the highest frequency, and 3 pi, 5 pi, and minus pi, of course. And it reaches to a minimum at pi, therefore we can say that it's a low-pass signal. It's a low-pass signal, and the low-pass region is repeating itself with 2 pi periods. And the high-frequency small responses are also repeating itself with 2 pi periods, from minus pi to 3 pi to 5 pi, things like that. Okay. Of course, I have already only drawn the magnitude. There is also a phase, but that phase is also 2 pi periodic, and I'm not going to draw that one anyway. Now, this thing, the discrete time Fourier transform, is therefore something 2 pi periodic. This was the first example that we have seen. Let's see some other examples, like the second example that we proceeded to in our continuous time Fourier transform domain or examples. Before proceeding, excuse me about that, let's see the other way around. We have covered this case. If A is positive and less than 1 case, will produce a low-pass signal. But wouldn't you agree that if A is between minus 1 and 0, whose magnitude is still greater than 1, but it's a negative number. If A is a negative number, then 1 over 1 minus A will be a large, the denominator will be large, therefore it will be a small number. For example, if A is minus 0.5, then what is 1 over 1 minus A? It will be 1 over 1 plus 0.5, which is 2/3, which is a small value like this. Whereas 1 over 1 plus A will be a large number, so it will go like this. Just the opposite. Let me open a red pen from here, and between minus 1 and 0 case, this red case is drawn like this. So when A is negative, this time the dashed red curve will be a high-pass signal. It looks to be high-pass. Is it really a high-pass signal from the time domain formula? Can you see that if A is negative, this boxed time domain signal has quite a lot of high-frequency components? Can you see those high-frequency components? A is negative. If A is negative, then its nth power will oscillate. For example, A to the 0 will be 1, which is positive. But A to the 1 will be negative. A square will be positive. A cube will be negative. A to the 4 will be positive. A to the 5 will be negative. So it will make oscillations. In fact, if you draw the two cases, It's not the example that I'm continuing, therefore, sorry about that. The high frequency case will behave like this. With a decaying exponential envelope, it will be positive and negative and positive and negative and positive and negative, positive, negative, etc. It is decaying with oscillations if A is less than 0 and greater than -1. That's why it's high frequency or a high pass signal that we have. However, if A is positive, it will only be an increase and then a decay. That's it. The first case. So the black curve, the original black curve, is a low pass version corresponding to a jump and then a decay, whereas the red dashed curve corresponds to a high frequency, which is an envelope like this, oscillating. That's why it is high frequency or high pass. Okay? That is something that we have to be careful about. Now we can proceed with the second example. Of course, since this is one-sided decay, the next example is it's not E, sorry, A to the absolute value of n. It's a two-sided decaying exponentials. Again, A in magnitude is less than 1. So the shape is not a jump and then a decay, but it is decays at two sides. It's increasing to 1 and then decreasing again back to 0. Decays at both sides. That's A to the power absolute value of n. What is the Fourier transform of this? The Fourier transform of it is with the formula n from minus infinity to infinity, x of n, that is A to the absolute value n, e to the minus j omega n, and that's the formula. There's nothing fancy about it. But because of this absolute value, we have to split this summation into two parts. The first part is n from 0 to infinity for all the positives, including the 0. And for them, A to the absolute value of n will be equal to A to the n, because absolute value of n will be n itself for positive n. A to the n, e to the minus j omega n. But of course now we have something else. That is from n from minus infinity up to minus 1. Now, what am I going to write? What is the absolute value of n for negative n? It's A to the minus n. The absolute value of n for negative n is minus n. E to the minus j omega n from the formula. Okay? So we have to split this summation into two parts corresponding to positive and negative n regions. And then we will have to continue. The first part, this one, is something that we have already covered. It's the answer to the first question, the top question. So the answer, let me write it. It is 1 over 1 minus a e to the minus j omega. Okay. For the second part, you need to put into parentheses and then again apply an infinite series, a power series. Still. But it's not from 0. It is not from 0 to minus infinity or from minus infinity to 0, but it is from minus 1. So one single term is missing from the power series. You have to subtract from the power series, the infinite power series, the origin n is equal to 0 term. When you do that, you will come up with this formula. E to the j omega in the numerator divided by 1 minus a e to the j omega. So what I mean is this. If the second summation, if this summation is from minus infinity to 0, then you would have a 1 over 1 minus a e to the j omega. So you have to subtract that one single term, and when you do that, when you subtract, because you're not going up to 0, but you're going up to minus 1. When you do that, when you subtract that term, you will get a e to the j omega divided by 1 minus a e to the j omega. So the summation of these two terms correspond to the discrete time Fourier transform of our signal, which is x of n is equal to a to the power absolute value of n. Now, since this signal is periodic, sorry, excuse me, not periodic, symmetric, I'm sorry. Since the signal, time domain signal is symmetric, from the properties of the previous chapter, from the continuous time chapter, do you remember that if you have a symmetric time signal, then the Fourier transform is real? Do you remember that? Cosine, for example. What was the Fourier transform of cosine? Two real impulses. So I would expect this Fourier transform to be real now, a real valued Fourier expression, omega expression. Is this thing real? But it's hard to see. You have to multiply. Since this left-hand side is the conjugate of the right-hand side, let's multiply with the conjugate both sides and then try to simplify and see whether we can obtain something real or not. And if you do that, of course, as expected, you will come up with a real expression. Honestly speaking, I would never ask from a student to simplify this Fourier transform expression so that it transforms into this in an examination. I would never ask it. Excuse me. 2a cosine omega plus a squared. So there's no j left here. And the e to the j omegas and e to the minus j omegas are combined in such a way that in the denominator we have a cosine without any j's. So everything is now real. It's a real entity. And a is less than 1 in magnitude, therefore a squared is also less than 1. And 1 minus something less than 1 will be positive here. And it will also be a positive entity in the denominator. So, this is the Fourier transform of our two-sided decaying exponential. And this exponential, again, you will probably not need to extract or find the formula in an examination. On the contrary, if you check out the books, the Oppenheim's book, you will see that there are typical Fourier transform pairs, tabulated. This formula is in the table, so you will have it already with you. You don't need to discover the formula again and again. You will have it with you during the examination while you're solving questions. And clearly it is 2 pi periodic. Why? Because cosine omega is 2 pi periodic by omega. And it's in the denominator, so it doesn't matter. The whole shape will have a 2 pi oscillation if you try to draw. And the final example, without going into a lot of details, technical details, I will just simply give you the answer. Because again, as I say, these are typical transform pairs, so they will be available to you in the tables. You don't need to reconstruct these formulas again and again. You will have them anyway. This is a pulse shape, rectangular pulse shape, which is 1 for time n less than or equal to capital N, and 0, well, else we can say, if it is greater than n. So, from minus capital N to plus capital N, it's all ones. discrete ones, and after that it is zeros. It's a rectangular box shape. Do we know the Fourier transform of rectangular shape from continuous time case? What was the Fourier transform? Is sinc, yeah. So we expect something like sinc here in the discrete time. X of e to the j omega, which is the Fourier transform of x of n, is summation. Inside it, I will have to write 1, but that 1 is valid only from minus capital N to plus capital N. Out of it, it is all zeros. So I start the summation from minus capital N up to plus capital N. It's not from minus infinity to infinity. Out of these bounds, it will be x of n will be 0. And here inside, it is now 1 times e to the minus j omega n. So it is this simple summation that we have to simplify, and the simplification is not so simple as you may guess. It requires a lot of steps, and at the end of the steps you will come up with this awkward looking formula: omega n plus 1 over 2 divided by sine omega over 2. Now this is the numerator is 2 pi periodic because it's sine omega scaled, and the denominator is also 2 pi periodic. In fact, it is pi periodic, the denominator, so it's also automatically 2 pi periodic. Their ratio, what happens to their ratio? This is an ill-behaving ratio, as you see, because when omega is equal to 0, sine of this, omega times 0 times something, will be sine of 0. And in the denominator, it is sine of 0 over 2, which is again sine of 0. Sine of 0 is 0. So the numerator and the denominator are both zeros. So what is 0 over 0? From sine theta is equivalent to theta for small theta. Okay? So using the Hospital's rule, as you suggest, when you apply this Hospital's rule, what you do is you get rid of the signs at the top and at the bottom. So you cancel the sign operators, you will have omega n plus 1 over 2 divided by omega over 2, where you can cancel omegas. And at the top you will have n plus 1 over 2 divided by 1 over 2. That is the value at omega is equal to 0. For all other omega values, how does it behave? Up to a point of pi, omega from 0 to pi, the denominator will have an increasing denominator effect. Therefore, the above sign will damp. It's like the sinks becoming smaller and smaller. You remember the sink shape? It was like this. So it behaves like this, but only from 0 to 2 pi, 0 to pi, or from minus pi to 0. So between minus pi and pi, it acts like a sink, like this, up to the point of pi. But after pi, due to the periodicity of the denominator by pi, it will this time start to decrease again. The denominator will start to decrease. So it will go on like this, become larger and larger again. And at 2 pi, it gets to its peak again. So this peak will repeat itself at 2 pi. And it will also repeat itself at minus 2 pi as well. So up to minus pi, it will decrease. And after minus pi to the left, it will increase again. So it is decreasing towards pi, increasing back at 2 pi. Towards 3 pi, it will decrease again. Towards 4 pi, it will increase again. So everything is 2 pi periodic, the shape. So it looks like a sink, but it's not a sink. It's a portion of a sink, sort of, which is repeating itself. because it has to be 2 pi periodic. It's the Fourier transform of a discrete time signal. It has to be 2 pi periodic, and indeed it is 2 pi periodic. A true sinc is never 2 pi periodic. It is just decaying arbitrarily. But this one is decaying and then increasing again, and then decaying and then increasing again. This is not a sinc shape, but it looks like it's sinc shape. Okay? At least from minus pi to pi within this range, it looks like it's sinc, and then it is sort of repeating itself. So that's what we have for the discrete time Fourier transform of the rectangular box shape. Now, I believe we can stop at this point because we have a few more examples, and then we will have the properties, just like the continuous case. So let's stop. We will continue tomorrow.